In this video, we're going to take a look at inverse functions. So a couple of the notes we need to write down are three basic steps we use when we're solving for an inverse function. The first step is to switch x and y. Your second step is to just solve for y. And the third step is to then write our new function as f to the negative 1 of x to represent that it is the inverse function and no longer the original function. Just to add to these notes, inverse of a relation, so like a set of ordered pairs, we don't need to solve for anything, so we're just going to use this very first step right here, and then that's all you need to do to find the inverse if you're just given a set of ordered pairs. So just switching x and y, we literally switch them and rewrite it. So negative 1, 3 becomes 3, negative 1. 4, 5 becomes 5, 4, and then 8, negative 7 becomes negative 7, 8. So that's all you'd have to do if that's all you're given. And then another big idea is that graphs of inverse functions always reflect over the line y equals x. So I wrote out a nice simple example. If we're given the function f of x equals 2x minus 1, I made a table of values, so I just picked negative 2, negative 1, 0, 1, and 2, and plugged those in and got my y values over here, and I graphed it in green. And then I found the inverse of f of x. So I used my original function, and then following these steps we just wrote down, I switched x and y, so literally just switch where they are written. Then I solved for y, so I added the 1, and then I divided both sides by 2, so I solved for y. But then I rewrote the function with the inverse notation. So f to the negative 1 notates that this is the inverse of this original function. It's no longer the original. And then I just wrote it out as 1 half x plus 1 half. So then I made a table of values, and I literally should be able to just switch x and y. So notice like that x and y are just switched and so on. So they're all switched. And then that's graphed in blue, and then I graphed the line y equals x to just show you what this is talking about. Anytime you have an inverse of a function, they should always be reflecting over that line y equals x. Alright, so let's look at a couple of examples real quick. So for our first example, it's just that really simple kind. If you're given a set of ordered pairs and you want to find the inverse, then you would very simply switch x and y. So I have 3, negative 1 if I switch them. I have 11, 4. I have negative 2, 7, and 9, 3. And that's all I would need to do if that's all I was given. For example 2, I'm given f of x equals 1 half x minus 5, and I'm asked to find the inverse. So using like this is your y, I'm going to rewrite it as x equals and then make my x become y. So that's the switch x and y step. And now I'm going to solve for y. So I need to add 5 to both sides. So I get x plus 5 equals 1 half y. Well, then I need to get rid of 1 half. So I'm going to multiply both sides by 2. I need to multiply everything over there on the left. So that's 2x plus 10. And then the 2 would go away when I multiplied by 1 half. So that's just equal to y. But then that third step when we're solving is to rewrite it in inverse notation. So that's just labeling that you have now found the inverse of this function f. That's all that that means. Excuse me. And then we're finished. Let's look at another one. Say we're given g of x equals x minus 3 squared plus 1. And we want to find the inverse. So switch your x and your y. And then we're going to solve for y. So I literally trade the x and the y. They switch places. So now let's subtract 1. So we get x minus 1 equals y minus 3 squared. Then I need to get rid of the square, so I'm going to square root both sides. So then I get the square root of x minus 1 equals y minus 3. Well, then I just need to add 3 to both sides, and I'm going to bring it over here where I have more room. So I have the square root of x minus 1 plus 3. Notice the 3 does not go underneath the radical. And then that's equal to y. So then I just need to add the right notation. I was given g of x. So now I need to write g to the negative 1 because I have an inverse of that function now. Equals what I found. So the square root of x minus 1 plus 3. And then that's it. So for number 4, I want to find the inverse of g of x equals x plus 4. And then I'm going to graph this original function and the inverse. So let's go ahead and find the inverse. So switch x and y. And then you just have to subtract the 4 to solve for y. And we are given g of x, so let's write the inverse of g of x is now x minus 4. So we are going to graph this original function x plus 4. So I could go to a y-intercept of 4, and I can use my slope of 1 over 1 and just graph that line. Then I'm going to use another color. Let's say I'm going to graph my inverse function with blue. So it's at a negative 4 for my y-intercept. Let's see, 1, 2, 3, 4 down. And then I have a slope of 1 again. So notice these lines, even though they are parallel, they are still reflecting over this line y equals x. Because that's that line that goes right through the middle, like we talked about, our linear parent function. So they reflect over y equals x, just like any inverse should do. All right, let's look at one more example. What if we're asked to determine whether each pair of functions are inverse functions? We're just going to use tables of values to check. So for this first function, f of x, let's check a table of values. Let's pick some values of x that would be easy to plug in here. So knowing that is a fraction, I'm going to try to help that to go away. So let's make x equal to negative 3, 0, and 3 to make these numbers easy. So negative 1/3 times 3 plus 3 would just give me, let's see, negative 1. The 3 would cancel out, and then you add the 3, so you just get 2. Then if we plug in 0, that would just be equal to 3. And then if we plug in, or excuse me, I was plugging in negative 3. That's what happened. So I would end up with a positive 1 plus 3 would be 4 right there. Then negative 1/3 times positive 3 plus 3 would equal 2. Okay, so in other words, we have negative 3, 4, 0, 3, and 3, 2. Those are our values from our table. I'll just write them again over here so they're nice and clear. Then let's check the other function and see if the inverse would work. So I am literally going to switch x and y and see if they make sense. So let's take negative 3, 4 and switch it and see if that would make sense for this second function right here. So if I were to plug in 4 for x, that would be negative 3 times 4 plus 9 if I plug it in there. So negative 3 times 4 is negative 12 plus 9 is equal to negative 3, which would give me the opposite of what I had in my green function over there in f of x. So let's check the second value. So let's switch 3 and 0. So if I plug in a 3 right here, that would be negative 3 times 3 plus 9, which is negative 9 plus 9, which does equal 0. So far it's checking out okay. Let's check one more point. So 3, 2 was my point for the green function for f of x. Let's switch it and see if that still works. So if I plug in 2 for x, so negative 3 times 2 plus 9, that would give me 3. So it does work that if we solve it with our table of values, we just check a couple of values, and we switch x and y, then they do make sense with the other function. So we would say in this case that yes, these are inverse functions, is what we could say. All right, so that's it for inverse functions.